Good afternoon. It is my pleasure to welcome Professor Bharat Ratna, Professor C.N. Rao, faculty colleagues and students of the center. It is a privilege to extend our hearty welcome to both the speakers, Professor Apoorva D. Patel of IISc and Professor Abhishek Dhar of ICTS. We thank you for accepting our invitation and giving lectures this afternoon. Late Dr. Raja Ramanna, he was the first chairperson of the Council of Management of this center when Professor C.N. Rao was the president, in fact, the founder president of the center. He instituted this endowed lecture at JNCASR in the year 1999 in honor of Dr. Raja Ramanna. Dr. Ramanna, as most of us know, was a leading Indian physicist, contributed immensely towards India's nuclear program for more than 4 decades. He held various crucial positions such as Director General of DRDO, Chairman of Atomic Energy Commission, Secretary of Department of Atomic Energy, Director of DARC, and also he served as scientific advisor to the then Defense Minister in the year 2000. As regards this lecture, I would like to thank Professor Rao for his efforts, for his visionary guidance in initiating the lecture series. This has been held successfully over the years. In 2019, we had a break last year, unfortunately. In 2019, the speakers were Professor Bhaskaran from IMS Chennai and Professor Sampath Kumaran from TIFR, and year before we had Professor Ogle and Professor Sriraj Minwala delivering the lectures. And going by the present circumstances, the meeting is mostly online. There are only a few colleagues in the hall here. So we'll get started with the first lecture. There are two of them. One is called the lecture, the other is called prize lecture. So first, the lecture will be given by Professor Apoorva D. Patel of Center for High Energy Physics, Indian Institute of Science, Bengaluru. Apoorva D. Patel is a professor at the Center for High Energy Physics at IISc. He obtained his master's in physics in 1980 from IIT Bombay, receiving the President of India Gold Medal for topping the class. He did his PhD in physics in 1984 from the California Institute of Technology, USA. I've seen one photograph on the internet where the famous Richard Feynman putting across his arm on the young Apoorva Patel. Very nice picture is there on the internet. Professor Patel has extensively worked on lattice gauge theory investigations of quantum chromodynamics. He is also notable for his work on quantum algorithms and the application information theory concepts to understand the structure of genetic languages. Today's the title is Quantum Technology, Directions and Prospects. Now the floor is open to Professor Patel. Please.
Thank you for inviting me to give this lecture. I am going to talk about quantum technology. It's a rapidly progressing and highly promising field for the future. And well, we are waiting to see what it can do, because many of these things may turn out to be unexpected. This arrow is not working. Fine. So the field of quantum technology is essentially defined by properties which are inherently quantum. And we have to make these inherently quantum properties to make new kind of devices, new kind of instruments, and then we will have the field of quantum technology under our control. What are these phenomena? Well, they can be quickly summarized as superposition, entanglement, squeezing, and tunneling of quantum states. These have been known since the birth of quantum mechanics and very well established scientifically. But Now the purpose of technology is to be able to control this phenomena and use it to do something new. And that is the conversion of known science into useful technology, which is exciting many people these days. And what do we expect? Well, here is a broad outline. I have put it with traffic signals, which says what is going to happen in what time frame. The first is a green signal, that means it's already happening. These are achievements in improving sensing and metrology to high precision. Then there is an orange light, which is on the verge of getting established. Those developments are going to be in communications and simulations. And then there is a stuff under red light, which is for the future. Of course, when we develop new technology and make highly precise measurements, it will have feedback on how well we understand the theory itself. So there will be consequences for foundations of quantum theory. And the final goal is to reach quantum computation, which will be a new counterpart to our traditional computers. What do we have to keep in mind during this? That the quantum dynamics, as we know, is highly fragile. It will work in cooperative settings very well, but not in hostile settings or environment. So we have to protect these systems very well, and this is where most of the development of engineering and technology is going. And it's not easy to conquer all the obstacles that are showing up. And what is likely to come in the future are some kind of hybrid devices. Some core task will be taken care of using quantum technology, and it will be embedded inside our existing classical systems. The most important thing to keep in mind is all our problems and their answers are classical. We can ask them by writing them on a piece of paper, and the answer also will be written on a piece of paper. Why is this so? Because we ourselves are classical creatures. So we can use quantum technology as an intermediate step, but we are not going to give up on the classical techniques which are well established. In this process, the classical technologies will also be pushed in new directions, miniaturization, integration, etc. And what has been dubbed as quantum supremacy is actually a moving target. And this foundation has been very well established. A lot of effort has been put in lots of different places worldwide, and we cannot afford to be left behind. So where are we? Well, based on my experience over the last several years dealing with various agencies, I can say that we are not doing very well. It's a long story, but essentially the infrastructure is inadequate. The trained power, manpower is lacking, and very little in terms of policy, in terms of what to do and when to do. So this is a topic which will take its own time for discussion, and I'm not going to spend much on it. Maybe in the question answer part at the end, I can say something more. What I will do is concentrate on what is happening worldwide. So let me come to the first topic that I mentioned, what is happening in sensors and metrology. The drastic difference in new kind of sensors that are being developed is in precision. And this is achieved by making correlated measurements, correlated across multiple detectors and multiple receivers. If you do that, then the quantum precision scales as 1 over n, where n is the number of devices or detectors. That is to be compared to the classical situation where the scaling of the central limit theorem is only 1 over square root of n. So there is a lot of things to be gained over here, and here are a list of examples. The atomic clock, it can be very easily improved in precision by order or maybe more than 1 order of magnitude. If you do that, the accuracy of devices which use atomic clock, for example, the global positioning system, can easily go up by an order of magnitude. There are new kind of materials in structures like nitrogen vacancy centers in diamond. They can be hyperpolarized, almost to 100%. What does that allow? That this kind of hyperpolarized centers can act as highly sensitive and robust magnetometers. So you can detect changes in magnetic field to a very high degree. And again, the gains are in orders of magnitude, and they can easily be expected to achieve a situation where our MRI scanners in a dedicated medical diagnostic center can be reduced to handheld devices, which can be used, say, for example, in an ambulance. So these are drastic changes. One can claim the same thing with electric fields. You can talk about networks. You can talk about interferometers. For example, interferometers using atoms can help in inertial navigations involving acceleration and rotation. You can even change the structure a little bit, so you can observe small changes in gravitational field. So you can detect things which are buried underground as well. And these are all different kind of sensors. You can combine electrical and mechanical phenomena, make transducers. They will have to involve both photons and phonon, and they will give you another set of devices with good sensing and control. All these things are small devices in the sense that the quantum core is actually not very large, and that is why they are becoming available already to some extent in the market. What is essential is there is a whole lot of control electronics in which this quantum device is embedded, and all that control electronics is classical, but it has to be developed. What about the software side? Well, there are new kind of algorithms. They are being developed. There's a lot of trial and error exploration of these algorithms, particularly in terms of handling large data. And this is becoming a big technological hurdle because now there are all kind of observatories and networks which collect a huge amount of data, and only some little bit of it is of interest. Most of it has to be discarded. And the question is how well you can pick out what you want. These are essentially problem of pattern recognition, classification, recommendation, and generic labels associated with these kind of problems are machine learning and artificial intelligence, where you train a particular device to do a particular job and then leave it to handle this large amount of data and see how well the job is done. All these kind of scenarios can improve quite a lot with algorithms which have quantum features. They don't have to be necessarily quantum, but we are just looking at a different strategy to solve the same problem. They include randomized algorithms, where actually instead of looking at probability weights, you look at unitary amplitudes, which are combined in a clever fashion to give new results. There is a wave dynamics-based techniques where interference plays a very important role, and its classical implementation, it plays a role of a device which can transfer energy efficiently from one place to another, and that can have a lot of applications in catalysis and even vibrational isolation. And there is a counter example that is there something which the quantum computers cannot do? And the answer to that is also yes. And this is becoming a basis of quantum safe cryptography, where you devise algorithmic schemes and use this to send messages. They are secured so well that even somebody who has all the power of a quantum computer cannot decipher or break this particular code. So all these things are new developments. A lot of it can be done classically and mostly in software. And this is where a lot of work is going on, because the hardware of quantum devices is still little bit further away, but the software is ready to go. There are a lot of developments in quantum communications. The basic principle again here is quite simple. What we need is to distinguish or discriminate one signal from another. That is essentially the point in encoding message. How well we can do that particular job? Well, the signals can be easily distinguished when they have no overlap. Mathematically, they means that the states are orthogonal. Now, all the states we use are not necessarily orthogonal, but there is a simple way to make them close to orthogonal, and that is to use multiple copies. So if you have a pair of states like psi and phi, they are vectors in some Hilbert space in quantum mechanics or ordinary space in the linear algebra. And the overlap is given by the angle between the two vectors, some cosine theta. But now if you take two copies of the same thing and ask the same question, what is the overlap? Well, psi cross phi and phi cross phi will have overlap, which is cosine square theta, which is definitely smaller. And by using many copies, you can make the overlap very small, and that provides you high distinguishability and resolution. The people who do this job very well actually are astronomers. They took pictures of the sky, which are not snapshots, but long exposures. And long exposures essentially makes these multiple copies available, and that is behind the idea of getting high resolution. So that is the underlying principle, and then there are many different components which are made or on the verge of getting established. They include quantum random number generators, which can be embedded now in mobile phone cameras. You can have single photon sources, which can fix the time resolution to very high frame in terms of distinguishability. You can have single photon detectors. Again, new materials like a two-dimensional graphene and molybdenum sulfide happen to do a very good job on it, and that is a crucial component for what is known as quantum key distribution. Then there is imaging with entangled photons, which is an upcoming area where you can improve the signal to noise ratio to a huge amount. And this has applications going in all kinds of directions. In a medical field, it can remove the radiation dosage, and in radar, it can reveal obscured objects. And of course, the long-term goal is to establish quantum internet, which will allow you to transmit signals without any errors along the way over long distances. This is a theoretical picture, and there are security questions which are always associated with communications. Those are not really handled by the quantum schemes. We still have to rely some extent on the classical machinery, for example, the authentication problem, how to get around the communication rate, and of course, certain things which the military always wants to do, that if you want to stop people from communicating, you just jam the signal. If the signal is jammed, there is nothing you can do, whether it is classical or quantum. So security is a little bit different problem, but yes, this communication field is also progressing very well. But the field which actually excited many physicists and chemists and even computer scientists decades ago was the field of quantum simulations. That there are lots of problems in nature which we are trying to solve using high-speed computers. But it is taking too long. Problems are too complicated for simulations. Generically, this has been dubbed as a sign problem because there are amplitudes which have opposite signs, and they can interfere destructively as well as constructively. And this kind of situation cannot be handled efficiently on the classical machines. So, lot of problems ranging from elementary particles to behavior of black holes, strongly correlated electrosystem, early universe, simulation of large molecules, they all fall in this particular category. And the hope is that if you have quantum hardware working, then these models of various quantum systems will be directly mapped into hardware. And the hardware itself will take care of the hurdles like the sign problem, and the simulation will become much fast. As a matter of fact, the claims are that it can even become exponentially fast compared to what we can do with conventional computers. And this is probably the field where there will be a true demonstration of what quantum devices can do. And quantum supremacy will really come into its complete strength. The applications are many, governing the design of new materials and new molecules, even going into as much detail as designing of catalytic agents and enzymes. And these are also things which are possible with not too large quantum computers, because these are systems involving a reasonably modest number of atoms, certainly not millions of atoms really. And the underlying principle is essentially quantum superposition or quantum parallelism, which our classical computers cannot do. They have to deal with this aspect one by one, and quantum parallelism will do everything in one shot and do it very fast. So what is the current status of hardware? It is being pursued both in terms of digital systems as well as analog systems. The digital systems are at the level where we have about 10 to 100 quantum bits available in a little processor. These are all noisy quantum systems. They do not have any error correction built in. They can do number of operations which are in the range of 100 to 1,000 before they end up getting completely destroyed by environmental disturbances. And we are learning how much we can do with this intermediate size system. And the analog systems are actually useful more towards the simulation part, which I just mentioned. You can directly model spin systems and molecular structures into structures like trapped ions and cold atom condensates. And how these trapped ion systems and condensates evolve actually tell us about how these interactions and reactions will proceed. And again, the systems are noisy, but they are at a stage where we are trying to get some signal out of this machinery. And the hope of this intermediate stage is that we are not yet at a stage where everything is going to get transformed, but we are learning a whole lot of new things, and that is giving us a glimpse of the opportunities for the future. And the target with all this playing around is to find problems which the computer scientists have classified as bounded error quantum polynomial in terms of the amount of effort involved. Goes under the acronym BQP. And these problems, or rather several problems of this type, are known to be hard on our classical computers, and belief is that they are reasonable to handle efficiently on the quantum devices, and we just want to find as many of these problems as possible. So this is a kind of very high level overview of all the kind of things going on. And to end, I will give a very simple example which only requires high school level knowledge. And this is a illustration of a problem called database search. This is what we do when we give a query to Google, find this thing. We don't worry about how Google quickly comes with a reply. But the underlying principle buried inside all this search is something we can understand in terms of very simple game which school children play. And that is to quickly arrive at a result from a large number of possibilities. For example, a name of a person. You keep on asking binary questions, which are yes or no. And the structure is arranged that if you answer yes, you go on one side. You go answer no, you go on the other side, just like in a dictionary. And by using the binary search, you can quickly arrive at the desired answer. The quantum strategy, it turns out, is different, or rather it gives a different answer for the same problem. And let me illustrate it in terms of a simple pictorial representation. The answer first, that using a binary question, one can unambiguously distinguish 4 objects. This is peculiar because we are all accustomed to using that you ask a binary question and you distinguish 2 objects, one for yes and another for no. But quantum dynamics says no, you can do better. And the result behind this is the wave dynamics. And our conventional Boolean logic is actually analog of particle dynamics. So let me show what happens in case of wave dynamics. You start with 4 objects. Initially, you don't have any idea about where the answer is. So you make a uniform distribution, completely unbiased. Then you ask a question. And the response to the question is what is different. You reuse the response as a sign, change plus to minus, corresponding to whichever component answers the question. Here I have taken it to be the first component which answers the question, and the sign of it actually flips. I have used a particular normalization where initial amplitudes were all half. It is a number so that if you take square of the amplitude and some more possibilities, it becomes 1. That is a standard scheme. Now, after you have flipped one of the amplitudes, physically, it can be achieved by a reflection where you reverse the velocity of a particle by, say, colliding with a wall. And after doing that reflection, you don't have to do anything. You just have to wait, provided wave dynamics exists. And what is the property of wave dynamics? That you have an equilibrium state, the average state, and if the damping is small, you will oscillate about the average state. So in the second step, the average happens to be a quarter, 1 of minus 0.5 and 3 of plus 0.5. And if you now allow the system to oscillate by half a cycle, going from one side of the equilibrium to the other side, maximum, it is called over relaxation. And then you reach a stage where the item which had a wrong sign gets an amplitude which is 1, and the other items fall to amplitude equal to 0. And that is the stage which you stop algorithm. The correct object which you are looking for has complete oscillation amplitude of the wave, and it is being singled out. And that is the way the wave dynamics finds the solution. One reflection operation, which is a binary question, and you can determine 1 out of 4. There is no error involved, provided the wave dynamics is perfect. So what is the use of such a simple scheme? Well, I found one. Where is it that the number 4 is more fundamental than number 2? The answer is we all have it. It is in our genes. So look at the problem of genetic languages. What is the task involved in the genetic machinery of every living organism? That you have to assemble molecules from an unsorted database according to some prescription. And this is what we do when we eat food, digest it into many individual components, and then reassemble it to make whatever you want. This reassembling process is actually a database search, because all the items are lying randomly all over the place and you have to find the correct one. Of course, you need a master template which tells you that this one is the right one to put, and then the next one is the right one to put, etc. The algorithm for doing that I already described. It was discovered by Love Grover, uses wave dynamics, and the surprising signature of this algorithm is what brings out the connection to genetics. That if you ask one question, you can distinguish 4 objects. If you ask 2 questions, the number is 10.5. If you ask 3 questions, the number you can distinguish is 20.2. When the number is a kind of fractional one, which means that there will be a little error, but the error happens to be small in these algorithms, say 1 part in 1,000. And these numbers are very important for understanding the structure of genetic languages. It is described why there are 4 nucleotide bases in DNA and why there are 20 amino acids inside protein. Then the question is, does the genetic machinery have the necessary ingredients to implement this algorithm? And then some primitive bacteria billions of years ago figured this thing out by some trial and error, certainly not by our high-level mathematics kind of analysis. And once it found the solution, it turned out to be the optimal solution and made it the universal language. And once you reach an optimal result, there is nothing better to do. The Darwinian principle will say that, okay, the natural selection will remain stuck at that particular place. So the question is it really what happened? And how can we answer this particular question? Well, that is the tough part. You have to develop the biological machinery to be able to observe these processes as they take place step by step. The intermediate dynamical steps have to be monitored, and if you can do that, that will throw us some idea about what really happened. We are not yet at this stage, but I am hopeful that something like that can be done in future. But the efficiency part is clear. It can be just counted in terms of simple numbers. That if you want to solve a database search algorithm, the full-fledged quantum algorithm solves with 2 qubits and 1 oracle call, binary question. A Boolean algorithm will require 2 bits and 2 binary calls, which means it's a factor of 2 slower in time. And the classical wave-based algorithm will require 4 modes, wave modes, but only one binary question or oracle call. This is the part which I just described pictorially earlier. So the wave algorithm is actually losing factor of 2, but in the space direction. And it turns out that biology has different importance for time and space. Time is highly important to be able to survive in the fittest game, while space is expendable. Plant doesn't care about producing millions of seeds, provided one of them can reproduce quickly and carry forward its land. So it is very likely that this advantage that you can lose in space but gain in time would have forced the genetic languages to take the structure which we observe today. And if we can understand this better, it will be a fantastic development. And I would stop at that and take any questions you may have. Thank you very much.
Thank you, Professor Patel. Do we have questions? How do we coordinate now? I mean, in the hall, anyone? Okay, on whatever platform plus YouTube. How do I know? Or you can show it to the speaker.
Is there a chat window or something like that in this?
They're just showing that. So kept it ready. Are there any questions there? Professor Patel, are you able to see the questions? Maybe you can take the number 1. I'm not able to see clearly.
No, I'm not hearing anything from any audience in terms of questions. If they can type in, then also I can see that. But right now, I don't have any chat box also.
You can show here on the screen. I'll be able to see.
Okay, so can I stop sharing it if that is needed?
Just a minute. How you trained Tathagat avatar? What? No. This is something irrelevant. How is it? No, I'm not too sure. Can you make sense of this? I'll just read out anyway. How you trained Tathagat avatar to see a child prodigy? Just I need your answers to tell my BTech students while discussing quantum mechanics.
Oh yeah, there is a chat box.
Okay, I'm glad you can make out. Yes.
Well, this is not a question relevant to me, whatever I see in chat box, not at least in terms of the present
Okay.
talks. I will skip that. You can contact me personally if you want to know.
Yes, Professor Amitabh Joshi is asking, time being precious relative to space in biology may not have been true when the genetic code was evolving. Could you hear me, Professor Patel?
Well, it is a kind of rule of thumb, if you want to say, but this is what Darwinian selection tells us, that, and which we can observe in a lot of phenomena, that if two species are competing, somebody gets a fraction of a percentage of an advantage. That advantage builds up exponentially over many generations, and it overwhelms the other competitor. And this is a empirical observation, but this is how time little advantage in time can gain very well, and space in this bargain, people are willing to lose in the sense that there is a high amount of parallel processing going on in all kinds of biological systems. It's not just one cell doing the same job. We'll have millions of cells doing the same job at the same time. And that parallel processing is essentially spending an effort in space to get a little bit ahead in time.
Okay, there is yet another question. I don't know how many we can take. Yeah, just a minute. Stay there. Stay there. Don't do anything. There has been news about China developing quantum computing for breaking classical computer-based cryptography. But you pointed out that there may be ways to make quantum safe cryptography. Can you please elaborate about it?
Yeah, it's not only China, it's probably in many other countries around the world. What has been proved theoretically that the common scheme of cryptography, which goes under the acronym RSA, is actually breakable if you have a quantum computer. Okay, so we have to give up on this RSA scheme once quantum computers become available. The question is there any other scheme which is not yet in place, but in principle it can be designed, which the quantum computers will not be able to break? So this goes back to the question about what is the power of quantum computers. And here again it is demonstrated that certain problems can be made easy if you have a quantum computer, but there are certain problems which still remain difficult, even if you have quantum computers. So the aim of the cryptography is to take one of these difficult problems and convert it into a cryptographic scheme so that the quantum computers cannot be used to break them. So these difficult problems are actually known. What is being undertaken nowadays, actually many groups around the world are working seriously on it, is to convert this difficult problem into a cryptographic scheme. And this actually requires hard work. You have to convert proofs, give guarantees of various types because this is a problem of security, and then give various kind of probabilities of how secure or how protected this kind of analysis can be. And that is the work which has been going on. It's actually a $1 million challenge which has been put out open for anybody to try their hands on, and people are working on it. The hope is that yes, we will have such a scheme ready in a few years, which will be complicated enough so that quantum computers will not be able to break it.
Okay, I have a quick point, something to check with you. As there are efforts to move away from the von Neumann architecture, improving on each individual bit is something, but there are also efforts to entirely move away from von Neumann architecture. So are there specific inputs from quantum technology?
Yes, means there is no hard and fast rule that you have to stick to von Neumann architecture. All our analog devices actually work differently. They are not digital. Digital structure is only the one which uses von Neumann architecture. And there are lots of processing capabilities of quantum devices which can be in the analog mode. And then you can use it like a neural network, for example. Or you can use it as a continuous variable processing scheme. And it is perfectly okay as long as you get to the final result. All we are ultimately interested is how accurately you can make some predictions. And yes, quantum computers will use architectures different than von Neumann architecture whenever necessary. They can also use von Neumann architecture in the digital mode, and that is also fine, but the other possibilities are open.
Thank you, Professor Patel, for the wonderful talk and discussions. Thank you. And we normally have a small honor to do here if you are here physically, but now it is going to be virtual. Okay. Thank you again.
Okay, thank you.
We will now move to the prize lecture by Abhishek Dhar. His technical issue is now sorted out? Okay. So Professor Dhar did his PhD at TIFR, Bombay, and then postdoctoral research at IISc Raman Institute and also at University of California, Santa Cruz. Before joining RRI, I think that was around 2002 or so. And in 2012, he left to ICTS. Now he's a professor there at International Center for Theoretical Sciences, Bangalore. His research interests are mainly in statistical physics, studying non-equilibrium problems. He looks at stochastic processes such as heat transport in classical low-dimensional macroscopic systems as well as quantum transport. He also works on active matter physics. Over the years, he has earned a lot of awards and distinctions. Some of them I'm going to read out. He was awarded the B.M. Birla Science Prize in the year 2004. He is elected fellow of the all three academies, Indian Academy of Sciences, the National Academy of Sciences, and the Indian National Science Academy. He was awarded the Ramanujan Fellowship in 2008. The same year, he received ICTP Prize. And the next year, he was awarded the Swarnajayanti Fellowship, and he was also awarded the Shanti Swarup Bhatnagar Prize in Physical Sciences. That was 2009. He is also chief editor of the Journal of Statistical Physics. Professor Dhar is going to talk to us on blast in one-dimensional cold gas from Newton to Euler and Navier-Stokes-Fourier. Professor Dhar, welcome.
Thanks very much for the introduction, and I'd like to thank JNC for the kind invitation to give this lecture. Okay, so I hope I'm audible.
Yes, you are.
Yeah.
Please
okay.
go ahead.
Okay, so I'm going to talk about this problem of a blast in a one-dimensional cold gas, and it's basically exploring the connections between microscopic theories and macroscopic theories. So this work is done with some really fantastic people, postdoc at ICTS, Shubhodip Chakraborty, and my student Santosh Gannappa, and a colleague at Boston University, Paul Krapewski. Okay, so these are the references. It just got published in PRL, and there's a longer paper in the archive. Okay, so let me. So here's the outline of the talk. So basically, there are these two descriptions of matter. One is the microscopic, which is the Newtonian description for classical systems, and then there's the macroscopic description, which for systems in equilibrium is thermodynamics. While when we are looking at dynamical phenomena, it's hydrodynamics. And the basic question that we address here is how well do they agree? Okay, agree, right? There are these two completely different descriptions of systems, and how well is the agreement between what they predict? And so I'll ask this question in the context of a blast wave problem. So this problem is basically a problem of, like, let's imagine there's a bomb blast, and so you have a very hot region, and it's kind of expanding into some cold environment, right? And we want to understand how this evolution takes place. So I mean, it's clear from this example that it's sort of an extreme example to test the validity of the hydrodynamic description. And this problem is kind of interesting because, okay, so it was studied first in the context of the atom bomb explosion in 1945, when people were doing various tests. And it turns out that when you write the hydrodynamic equations to describe this system, you can actually solve the Euler equations exactly. Okay, so this is very solution by Taylor, von Neumann, and Sedov, and I'll talk a little bit about that. Okay, and so what we'll study is the blast wave problem in one dimension, where it is even an extreme example where you might worry whether hydrodynamic description is valid or not. It's already known that there are some anomalies in one dimension. For example, heat transport is anomalous, and Fourier's law is not valid in strictly one-dimensional systems. And so we'll look at one-dimensional this blast problem. And what I'll show you is comparisons between Newtonian molecular dynamics simulations of a one-dimensional hard particle gas, and compare them with basically the predictions of hydrodynamics. And hydrodynamics is either at the level of Euler or at the level of Navier-Stokes and Fourier. Right. So this is the basic question that we are looking at. So let me just remind you that about these two descriptions of matter. So the microscopic description is you look at n molecules, let's say moving in one dimension, and then you describe it by the positions of all the particles and their momentum. So Q's are the positions and P's are the momentum, n particles. And typically you have a Hamiltonian which describes this system, which has a kinetic energy part and a potential energy part. And then you write Newton's equations for the evolution of this degrees of freedom. Okay, so this is Newton's equation written in this Hamiltonian form. And so this is the microscopic description. And the macroscopic description, the first thing one thinks of is equilibrium statistical physics. So there what we know is, like, if you take a gas, I mean, you don't really care about all the microscopic degrees of freedom. It turns out that a good description is in terms of the so-called conserved quantities in the system. And for a gas in a box, it's the number of particles, the volume, and their total energy, and the total momentum of all the particles in the box. Okay, and what Boltzmann and Gibbs told us is that given this constraints of energy, volume, and number of particles, and so on, you can compute something called an entropy function, which if you know the Hamiltonian, then there's a constant energy surface in 2n dimensional phase space, and you just compute the area of this surface, and you take log of the area. So that is this k log omega and times the Boltzmann's constant. So this gives the entropy of the system given the microscopic Hamiltonian. Okay, so this is the connection between the microscopics and macroscopics. And once you know the entropy, you know everything, all equilibrium properties of the system. For example, its equation of state, its specific heat, compressibility, etc., and so on. Okay, so this is for systems in equilibrium, and in out of equilibrium systems, it's sort of an extension of this idea of equilibrium. So for example, consider systems like gas flowing through a pipe or water boiling inside a beaker and so on. So what is the useful way of describing such a system? So if you look at the gas flowing in a pipe, you can of course look at the molecules. But then what you say is that we want a description in terms of the conserved quantities. Okay, so the conserved quantities are again the number of particles, the momentum, and energy. But now you look at like small cell. What we know is that there's some variation in space. So you look at small cells of, let's say, size L, and you just count the number of particles, the total momentum, and total energy of all the particles in this cell. And then once you know this, then you have this basically these three hydrodynamic fields: density, velocity, and temperature, or momentum and energy, which describes the system. Okay, and we expect that locally this system, these three variables will satisfy the thermodynamic equalities and so on, but they vary in space and time. Okay, so that's the description for systems out of equilibrium. Locally you have equilibrium, but this equilibrium state varies slowly over space and time. Okay, so now why do this very slowly? Because they are conserved quantities, so they have to change slow. I mean, they can only change through boundary region, so that's why changes are slow, and that's why these are the quantities that you care for in the hydrodynamic description. Okay, so the idea is that these fields evolve slowly, while all other fast degrees of motion lead to effective dissipation and noise that is seen by the slow fields. Okay, so this is the prescription to go from microscopics to macroscopics. You basically, if you know all the positions and momentum of the particles, right, yeah. So if you know all the positions and velocities or momentum of the particle, then the density is just given by counting the total number of particles in this region and dividing by the length. and that you can formally write in terms of some delta functions. Okay, so given qj's and pj's of all particles, you can construct the three fields, the macro hydrodynamic fields that is used in the hydrodynamic description. Okay, so now we know the Newton's equations of motion for the microscopic variables. So the natural question is, what are the equations of motion of these coarse-grained fields, which we expect to be the only relevant degrees of freedom. Okay, so this, of course, one knows that these are the Euler and Navier-Stokes equations. And these equations were, of course, written a long time. And when they were written, one did not really worry about what is the microscopic basis. So these equations were written purely phenomenological. So the first equation is just conservation of number of particles. Derivative of density is divergence of density into velocity. And the second equation is conservation of momentum, and the third equation is conservation of energy. Okay, and in this equation, I have so these equations have the form of a continuity equation. So it's like del rho del t plus divergence of a current is 0, and the current has two parts, sort of a deterministic part and a dissipative part. Okay, so the dissipative parts I've written in red, and if you drop these terms, so then you just the particle current is just rho times u, that momentum current is rho u squared times the plus the pressure, and this is the energy current. So if you drop this the red terms, then what you have is are the Euler equations, and if you include the red terms, which has a viscosity term and a heat conduction term, then these are called the Navier-Stokes-Fourier equations. Okay, so normally in fluid dynamics, one is the Navier-Stokes equations are more popular because quite often you don't care about temperature variations, and you just write the first two equations. But if you care about temperature variations, you have to include the heat conduction term. Okay, so this is, you should remember that when I say Euler equation, it just means the black terms, and when I say Navier-Stokes-Fourier equations, it includes the dissipative terms. Okay, now in this equation there are, here there's this epsilon, which is basically includes the internal energy density in the system and the flow energy, just the flow, the kinetic energy due to the flow. Okay, so the total energy is separated into a sort of advective part and a part which is internal energy. And this internal energy again is given by thermodynamics. It depends on the local density and temperature. And then there's a term P, which is the pressure. Okay, so finally there are three independent fields, rho and velocity. In term, we have replaced momentum by velocity, and instead of energy density, we look at temperature. So these are the more physical fields that one can look at. Okay, and the connection to microscopics is that this, of course, you can obtain from equilibrium statistical field. So these are the equations of state and the energy. And then there are the so-called transport coefficients, the viscosity and the thermal conductivity, which are given by, so if you know a Hamiltonian of a system, then you can use linear response theory and the Green-Kubo formulas to compute these objects. Okay, so now...
Can I ask a question?
Yeah.
Sir, in the previous slide, like these red terms, are they coming because of some sort of averaging over the initial? I mean, you have average over the initial condition, right? I mean, in a sense.
No. So this comes even if you have just a single realization of the microscopic system.
Oh, even for single realization.
Right. Yeah.
So what exactly is the use of average over initial condition? How does that
You
change
don't have
the
to do an average over initial conditions.
thing?
Right. Yeah.
And the pressure term.
I'll do that maybe when I describe the microscopic model.
Okay, fine.
Okay, so now the basic question we are asking is how good is this hydrodynamic description? So now, of course, one question is there a rigorous derivation of hydrodynamics from Newton's equation? And this is actually part of Hilbert's famous set of problems. This is his sixth problem, and so far it's unsolved. So in physics, of course, this is a sort of a mathematician's perspective. In physics, from a physics approach, if you start from Boltzmann theory, there is a sort of derivation of hydrodynamics. But then you can ask how is Boltzmann connected to Newton, and that is still not completely, the steps are not completely clear. Okay, so recently there's some work that we have done on this method using a method of projections, trying to derive hydrodynamics, but I'm not going to talk about this today. So, but basically the question is how good, accurate is this hydrodynamic description, and what are the limits of its applicability? Okay, so surprisingly, there are very few precise numerical verifications of this equivalence, and that is what I'll talk about today. So there are earlier works on hard sphere systems, and I'll mention briefly those work. Okay. So the case where we examine this is the blast problem, and let me just give a brief history of the blast problem. Okay, so this was first studied at the time of the Trinity atom bomb explosion in 1945. And so here is the first picture of the atom bomb in that was taken that took place in Manhattan, sorry, in Los Alamos. And you can so this is a snapshot at like I think millisecond time scale of the explosion at various times. And what you see is a shock front which is slowly expanding, right? So there's a very hot region and which is expanding, and so there's some growth with time of this the size of the explosion. So so this is what you see, and so one of the first interesting questions you can ask is how does this length scale grow with time? And it turns out that you can actually do a very simple dimensional analysis which tells you how this grows with time. Okay, so this is quite amazing. I mean, you ask what can it depend on this size of the bomb, this explosion, and you realize that it has to depend on the total energy of that's contained in the blast, and it has to depend on the density of the ambient atmosphere, right? So let's call that rho infinity, and total energy is E, and it depends on time. And then basically, if you just do this usual dimensional analysis, what you find is that this radius depends on time in this way, okay, where d is the dimension in which you are working. You can do it in do this analysis in any dimensions. Okay, so if you now in 3 dimensions, if you do this computation, what you find is that the radius grows as t to the power 2/5 with some prefactor out here. And in 1945, if you just use this data, if you look at this, how this R goes with time, this is what is plotted here, and you find perfect agreement with this formula. Okay, and in fact, you can use the data to extract this energy here, because the slope also and you can use this to extract the actual energy released in the explosion. And this is one of the best estimates of actually of how much energy was released in the explosion. So this, I mean, sort of maybe a nicer example, if you don't like bombs, is that these equations are also actually can be used to study how a supernova explosion takes place and what is the energy released in a supernova explosion, just by looking at like how does the explosion grow at time at a present time. Okay. Okay, so now let me talk about like what else do we want. So this is just I said how the front grows. So what else are we interested in? So I mean, outside the this front, there's cold gas which is undisturbed. So some of the interesting questions are what are the profiles of the density, velocity, and temperature inside this blast, right? I mean, you can ask yourself, is the temperature maximum at the center, or is it a maximum at the edges? Where is the velocity fastest, and so on. So for this, what Taylor, von Neumann, and Sedov did was just solve the Euler equations with the initial condition that you have some extremely hot region. Okay, so so in this case, what they discovered is that there is a very nice self-similar solution at that you can at long times. Okay, so self-similar means basically that rho depends on the position and time through but you can sort of get a scaling form where rho depends on r and t through the ratio r over t to the power 2/3. Okay, so there's a scaling form. That's what self-similarity means. And we know the size of the shock, which is t to the power 2/3 into some constant. And the idea is that the self-similar solutions looks like this. Okay, so the density depends on some scaling function of z, where z is x divided by the size of the shock of the blast, and then similarly for the velocity field and the temperature field. Okay, so there basically you can write the exact complete solution in terms of these three scaling functions g, v, and z. Okay, and then so at long times you don't care about the initial condition. All you need is the total energy that you put, and then there's a shock, so you have to use some boundary conditions at the shock front, which are known as Rankine-Hugenoit boundary conditions in fluid dynamics. And using this, basically, if you plug it into the Euler equations, you get some nonlinear equations, which quite amazingly one can solve exactly, and you have a complete description of how the shock evolves. Okay, so these are some references where this is done in like discussed in great detail. Okay, so now let's ask how does it compare with microscopics, right? So this has been studied earlier by several people, and but mostly in 2 and 3 dimensions. And this is what it looks like. Okay, so you have so this is a simulation. This is a really nice simulation by this group from Mat Science, Rajesh and his student, who looked at at 1 million particles, hard disks. And what you do is initially all the hard disks are at rest, and at time 0 you just have 4 disks which start with some velocity, and you look at how the disturbance evolves, right? That's the blast. And you look at it at various times, and you can see that there are less particles at the center, more particles at the end, and you can compute what is the temperature profile, what is the velocity profile, and so on, and compare with the predictions from the Euler equations of TVNS. So what they found is actually there are significant deviations from the predictions of TVNS. And so what we thought is actually, so in higher dimensions, there are various issues that you don't know the equation of state exactly. You have to do some virial expansions and so on. So there's a lot of ambiguities. So it's a more difficult problem. So what we looked at is the case in 1 dimension of a gas of hard point particles. The advantage is that the equation of state is just ideal gas, and this, so it's exact. You can solve the TVNS equations exactly, which is what I showed just now, and it's much easier to do the simulations. Okay, so let me just come to the details. Okay, so this is the microscopic model. The hard part, so you have n particles with so this is the microscopic. If you are looking at a microscopic model of the blast, this is what it looks like. You have n particles with positions and momenta and mass. Okay, so here it's important that we take, you can just take them alternate masses like m1, m2, m1, m2. If they're equal masses, then it becomes what is known as an integrable model, which doesn't have any hydrodynamics. Okay, so you have to make them sort of in a non-integrable model with good ergodicity property, sort of equilibration properties. Okay, so so this is why we choose this alternate mass model. And then what you do is at time 0, all the particles are at rest except a small set of particles at the center. Okay, so the initial set of particles, the size and all, it really doesn't matter at long times. You could just take 4 particles which are and you choose their velocities from some distribution corresponding to some temperature. And then you just look at how this system evolves. Okay, so here I've just written the dynamics of the system. It's just hard particle collisions. Whenever 2 particles collide, they conserve their mass, their momentum and energy, and so the new velocities change in this way. Okay, so this is the initial density profile that we start with. It's just like the macroscopic initial density profile. And so if at a microscopic level, if you just look at what are the trajectories of all the molecules, you'll find that it looks like this. Okay, so this is time and this is space, and I'm plotting the trajectory of different particles. And so what you see basically is that as with time, more and more particles start moving. And so this is the region where particles are moving. And so of course you can track each particle, the dynamics of each particle. And here I've also drawn this dashed line, which is actually the prediction from the hydrodynamic description, this R of T. Okay, and you can see that even at the level of a single realization, the edge of the blast follows very closely what you predict from hydrodynamics. Okay, so now of course we do some like we construct the fields we are interested in, this density, momentum, and energy using this prescription. And so here I have some average over initial conditions, and like someone asked, is this average required? So right now I'm doing it because it gives better statistics, but I'll show a result where I don't do this average and you still get the same results. Okay, so this is just to get things smooth. Okay, so now if I from the microscopic dynamics, if I evaluate these three fields and plot them, so these are heat maps which basically show where it's maximum and where it is minimum at different regions in space and time. Okay, so this is time and this is space, and here you can see that the density is, so if you take any time cross section, you can see that the density is minimum at the center, it's maximum at the edges. The temperature is maximum at the center, and then has some profile. And so now let's look at a given time, we can look at what are the profiles of these three conserved fields and how do they evolve in time, right? So this is what it looks like. So this is the density profile. It's maximum at the center, very low at the minimum at the center. And this is at an early time, and this is how it's evolving. Okay, so at time 0 it's uniform, but then at some long times it evolves in some way. And similarly the velocity and temperature. And now we want to ask, does it have the scaling form that the Euler equation predicts? Okay, so we have to scale x by t to the power 2/3, and that's this variable z, and then look at all these plots. Okay, and when you do, you find this remarkable collapse of all the data, and out here the dashed line, it shows the exact scaling form solution of TVNS from the Euler equation. Okay, so for all three fields, you find very good, I mean, quite remarkable agreement between the predictions of hydrodynamics, Euler equations, and the microscopic simulations. Okay, however, you find at the core of the blast. So let me just also say that even at the shock front, you get extremely good agreement, and in fact, it gets better when you go to larger times. Okay, but at the core of the blast, there's a discrepancy. The exact solution from TVNS predicts a divergence at the center, which is of course unphysical, and the actual simulations show that it remains finite. Okay, so we want to understand this, and this can be understood basically by now looking at the contribution of the dissipation terms. So these are terms that we had neglected when we wrote the Euler equation, and we can neglect them because at the scale we are looking, these terms are irrelevant. Okay, but now when we see that there's some discrepancy, we have to re-examine whether it was justified in neglecting these terms. And so we compare, let's say we compare this heat conduction term to the terms on the left hand side. Okay, so let's say we look at the ratio of this dissipation to the kind of the inertial terms, and so when we compare, we use the exact solution that we know from TVNS for the temperature and density profile, and we make this estimate. Okay, so while making this estimate, we have to know how the thermal conductivity depends on density and temperature, and this is not so well known. So we know we use some results from like earlier numerical studies, and that's why you get this strange powers out here. But what this tells us is that, okay, so now the question is, when is this large? Okay, when do these terms become comparable to these terms on the left hand side? When is it that dissipation becomes important? And we find that this becomes large in a region which grows with time in this way. Okay, so we have the entire blast which is growing at a scale t to the power 2/3, but in a smaller core region, which is t to the power 38 by 93, which is much smaller than 2/3, there's a different, we now expect a different scaling because these terms were important, right? So, and so now we have to do an analysis including these terms. And so this, of course, now it's difficult to solve, find an exact solution. So what we did is a numerical solution of this full set of equations. Okay, I think I have 2 minutes. Okay, so that's good. Okay, so you can solve the Navier-Stokes-Fourier equations numerically, and then you find these solutions. And again, they look very similar to what we saw in found in the numerical solutions. Sorry, in the molecular dynamics simulations. And but now one good thing is that you don't see a divergence of the temperature at the origin. Okay, so now we try the scaling again, and we find that the divergence that you see in the Euler equation is now avoided. So now let's finally compare all three methods. Okay, simulations, Euler equations, and Navier-Stokes. So what we find is, so let's just look at the temperature profile. I mean, the other fields, it's this sort of a similar thing. So the dashed line is the Euler equation, the exact solution of TV and S. The blue line is what you get from a numerical solution of the Navier-Stokes-Fourier equations, and the red is the microscopic simulations. Okay, so I mean, this is now better than the Euler equations, but we still don't have exact agreement in this small core region. Okay, so I mean, you should remember that this core region is really small if you look at it in the actual scale. Okay, so even on and it shrinks with time if you plot it on this scale. Okay, so it's so it's really a very small region where you have disagreement. Okay, so I won't, I'll skip this. So this is what I just said, that if you do with a single realization of this system, do no averaging over initial conditions, you still get the same results that I described earlier. So, I mean, this is of course important because, I mean, when we look at real systems, we don't do an average over ensembles, we look at a single realization. Okay, so I will conclude. So basically, I talked about two descriptions. So there are two descriptions of air in the room. One is an atomistic and one is a continuum description. And the question is the hydrodynamic description always valid? So the other examples where people worry about this is in extremely dilute gases, where it's known that you have to do kinetic theory and you can't rely on the hydrodynamic description, right? So we tested this question in the problem of this blast wave, which is nice because for this, particularly for this 1D gas, there's an exact solution, and so you can do a better comparison of things. Okay, so this particular system is sort of has very good equilibration properties, and we find this remarkable agreement with between simulations and Euler and some deviations. Okay, so this question remains: can we get even better agreement between microscopics and macroscopics? And the main difficulty is that we don't know the transport coefficient so well. In particular, we don't know that dependence on density very well. Okay, so the dependence on temperature is known exactly, but the dependence on density is not so known well. Okay, so so finally, these are the references, and like I said, there's also related recent work on a microscopic derivation of hydrodynamics, which also has appeared recently. Okay, so thank you, and I'll be happy to take questions.
Thank you, Professor Dhar. What about questions? Just simply unmute and ask, is it? Okay. First in the hall, anyone? All right, so people online may ask now. You are your own control, so just unmute and see to that we don't have overlapping, questions being asked. One by one, please.
Abhishek, can I ask?
Yeah.
Yes.
So, so in terms of deviations from hydrodynamics, you're finding it to be most in the low density region, right? In the
low density, yeah, that's true. At the core, the density is also low and temperature is very high.
Right, but you presumably there is some role played by fluctuations. You didn't say anything. Is that something that one should also be looking at?
Okay, so I mean, of course, like fluctuations would be going beyond hydrodynamic description, right? So that, I mean, so it's possible that that could be a reason. Like, so there are, I mean, so there are various possibilities why this is breaking down, and that could be one possibility. I mean, right? Yeah, that's like, and then you'd have to go to a kinetic theory description.
Right. Right. Okay. No, I mean, you only mentioned the low density aspect of it, but this presumably goes hand in hand with fluctuations being large by some measure.
Right, yeah. Yeah, but basically you're, I mean, at some level it should agree, right? I mean, like if you do sufficient coarse graining. But what you're worried about is like because there might be too few molecules in a volume, and so right, yeah, that's of course a worry. I mean, so the comparison might get harder. That's true. Yeah.
Okay. Thanks.
Okay, thank you, Shrikant. Anyone else? Do we have questions on YouTube? No, no questions on YouTube. So I don't think we have any more questions. Thank you, Professor Dhar. And as usual, the honor will be virtual, and none in the audience will get to see that. So this is the time I thank both the speakers now and Professor Rao, and also everyone in the audience, online and also here. Thank you very much. Let's conclude now, and have a nice evening and safe stay. Thank you.
Thanks.